Hello. We are looking at binomial experiments. So this goes off what we did the other day. The other day we were given the probability chart and we were figuring out, all right, how many chances that there's over 3 eggs broken, things like that. And so we had to use the probability chart there. Today we're taking a step back and we're actually going to make the probability chart. Right? We have this great handy dandy formula that we can use to help make the chart. So we got a lot of jargon up top, but let's just jump right in and kind of work this out. All right, so here's our situation. During the Christmas season, the Bruce Springsteen version of Santa Claus is Coming to Town can be heard on the radio frequently. As a matter of fact, the probability that you hear that song on the radio during a random December day of listening is 0.76. All right. Let's suppose we decide to listen to the radio for the next week. Create a probability distribution for the random variable x, where x is the number of days you heard Bruce Springsteen's Santa Claus is Coming to Town. Okay, so if we're talking about a week, in this situation, we have you hear it 0 days a week, 1 day a week, 2 day, 3 day, 4 day, 5 day, 6 day, or on all 7 days during the week. Now we have here is hearing it is 0.76. 0.76 you hear it. On the flip side, 24% you don't hear it. All right, so here's where we jump into our big formula here. All right, so here's how this works. All right, so on the first day, there's 7 options, right? We've talked about 7 total days. All right, so you have 7C0, the probability of hearing it, points times 0.76 to the 0 times 0.24 to the 7. All right, 7C0, 0.76 to the 0 times 0.24 to the 7th. All right, so onto our calc. 7C0, obviously we don't need the 0.76. We don't need that because that's just nothing really. Well, it's 1. 0.24 to the 7th. And we get an extremely tiny number, 0.00045. Am I off by 1 0? 1, 2, 3, 4. Yep, one more 0. All right, so the likelihood of you not hearing that song a week, very slim. Right? So 7C1, 0.76 to the first, times 0.24 to the 6th. Right, so those exponents always have to add to 7. Now, the easy thing is on your calculator, just copy and paste. Slide up, copy it, change to 7C1, raise to the first, raise to the 6th. And again, we get another super small number, 0.001. Yeah, I'm not even going to write anything. 0.001. Tiny. 7C2, 0.76 to the second, times 0.24 to the 5th. Copy, paste, and so on. All right, we get 0.0096. 0096. So we repeat this over and over again. 7.3C, 0.76 to the third, 0.24 to the fourth. 7C4, 0.76 to the fourth, 0.24 to the third. 7C5, 0.76 to the fifth, 0.24 to the second. 7C6, 0.76 to the sixth, 0.24 to the first. 7C7, 0.76, 7 to the 7th, 0.24 to the 0, meaning we heard it every single day this week. Right, so as you go through that process, you'll figure out these numbers. So we get, for 3 times, we get 0.051, 4 times, 0.1614, 5 times, 0.3067, 0.3237, and to hear it every single day, 14.65% chance that we hear it every single day. All right, so that's our probability distribution. Now what we've learned is, all right, if this is x and this is p of x, if we want our expected values, we multiply x times p of x, right? So we could do that whole process, x times p of x, and we could figure out exactly what we have. So if we made an extra row, which I guess I'll make it over here, x times p of x, we got 0, 0.001, 0.0096 times 2 is 0.0192, 0.051 times 3, 0.153, 0.1614 times 4, we have 0.2456, 0.3067 times 5, 1.5335, 0.3237 times 6, 1.9422, 0.1465 times 7, 1.0255. If we add all those up, 0.001 plus 0.0192 plus 0.153 plus 0.2456 plus 1.5335 plus 1.9422 plus 1.00255, we get 4.92. Oh, I messed up somewhere. No! My math is somewhere off. Found it. My bad. That's times 4.6456. So let me just change that number in my calculator. Even teachers make mistakes. 6456. And we get our expected value to be 5.32. So the idea here is that if we listen every single day to the radio, it's expected that we hear this song on 5.32 days. So between 5 or 6 days. Right now, what we talked about the other day was we don't have to go crazy and make this full chart. We have our calculator, right? One thing on the calculator we know is that the expected value is our average, right? So if we just did the calculator and got the expected value, we could get that number, right? It'll give us the mean. The mean's the expected value. The second thing is we need the standard deviation. We're always asked for that, right? So this is where we use our calculator. So as we talked the other day, x is L1. P of x is L2. We're going to type all that information in. Right, so we hit stat, we hit edit, right? We got 0, 1, 2, 3, 4, 5, 6, 7 down that right side, down that left side for L1. We're changing the L2 to make sure that every x value matches up with its correct P of x value. Right, every x value has to match up with these. Right, so I got all those numbers typed in. Now, once everything's typed in, we leave, second quit. We hit stat. We go over to calculate. We go one variable statistics. And what we have to make sure is the list is L1 and the frequency list is L2. Not every situation we do does that scenario have to hold, but for most of them it has to hold. We go down to calculate, and we'll see what we have, right? So our calculator, the x bar, 5.32. The sigma x, right? Sigma x is the expected value, right? Then our standard deviation is this standard deviation. So we got 1.13, right? So what does that mean? That means that 68% of the chance here on a normal distribution curve is between 5.32 plus 1.13 or 5.32 minus 1.13. So I guess in that scenario, 68% of the people will hear this song between 4-ish days and 6-something days. So that's the scenario we have here. So kind of recovering what we got going on. With the calculator, we don't have to do this. The calculator does that for us. I was showing it one time, but it's just good to see. Moving forward, we got some even faster things that we could do. So this bottom problem here is on the top of the next worksheet. Binomial distribution, mean and standard deviation. So we have this exact same formula that we're talking about. We got this scenario. Suppose that Louie and Leach managed to manipulate a coin in such a way that it lands on heads with a probability of 0.7. So we got 0.7 success. It lands on tails, 0.3. 0.3, in this case, fail. All right, suppose you flip the coin 5 times. We need a probability distribution and calculate it. All right, so if we're looking for probability it lands on heads, it could land on heads 0, 1, 2, 3, 4, or 5 times. And just like before, we could do the whole big formula, which we got up top, where we'd have 5C0, 0.7 times 0 times 0.3 to the 5th, to get our P of X. So if I'm going through that process on my calculator, trying to get the I got 5C0 0.7 to the 0 times 0.3 to the 5th. I got 0.0024. And I repeat this process over and over. 5C1, 0.7 raised to the 1st, 0.3 raised to the 4th, 0.02835. 0.5C2, 0.7 to the 2nd, 0.3 raised to the 3rd. I got 0.1323. 5C3 to the 3rd, to the 2nd, 0.3087. All right, do it 2 more times, just get our situation settled here. 0.36015. And last but not least, 5 heads. I meant 5, what do you want? 5 heads in this scenario. We get 0.16807. All right, so if we wanted to find our expected value, we add them all together. If we go to the calculator, our expected value, which is our average, in this situation is 3.5. We would have to do the whole x times p of x and add those numbers together to get 3.5. But our calculator does it for us. Standard deviation, our calculator tells us 1.024. Now, the shortcut of all shortcuts, the shortcut of all shortcuts in this scenario is this. On the next page, on the top, it got our shortcut formulas. So our shortcut formulas, well, mean, which is x bar, which is the expected value, is the n times p. So the simple idea here is n is 5 times 0.7. 5 times 0.7 is 3.5. Yikes. Look how fast, look how quick to the point that formula is. We were doing that whole crazy setup on the previous page. This is the fastest way to do it. The amount of trials times the probability of success gets you the expected value, gets you the average, which is the mean. The standard deviation, even simpler here. Standard deviation is square root of NPQ. So it's the square root of 5 times 0.7 times 0.3. 5 times 0.7 times 0.3. There we have our 1.024. right? These are our two shortcut formulas. They're great, they're helpful, right? It's important to understand why things come from, but on the next page, it's just quick, straight to the point. Suppose the probability that a freshman girl would go on a date with Will is 0.4. He has 7 girls. 7 times 0.4. The likelihood that a girl says yes is 2.8, right? He has 7, 2.8 of them will say yes. What's the standard deviation? Meaning that 68% of them are there. Well, 7 times 0.4 times 0.6. Square root of 7 times 0.4 times 0.6, right? 1.3-ish, 296. Yeah, quick, straight to the point. We don't have to make those charts. We don't have to do all that work, right? This is the quick way to find the expected value and to find the standard deviation.